All right, I'm going to share my screen. All right, folks, welcome to another session. We'll continue from where we left. We're still discussing linear algebra, and I think we shall be discussing linear algebra at least for a while. Of course, along with linear algebra, we shall be doing other things as well. Before I continue with the session from where we left previously, let's start with an anecdote. This takes us to summer of 1949. I'm going to read that paragraph for you. It's a bunch of paragraphs. I'll probably take a minute or two to have it read to this audience. So this was a late summer of 1999. Professor Vasily Leontiev was feeding the last of his punch cards into the university's Mark II computer. The cards contained information about the US economy and represented a summary of more than 250,000 pieces of information produced by the US Bureau of Labor Statistics after 2 years of intensive work. Leontiev had divided the US economy into 500 sectors, such as coal industry, automotive industry, communications, and so on. And what he did was, for each sector, he had written a linear equation that described how the sector distributed its output to the other sectors of the economy. What this means is, for example, let's say you work for an IT firm, which means you're participating in the economy of, say, the sector called information technology. But then what you also do is, when you're at office, you're probably ordering pizzas at the Domino's. So in a way, sitting at office, working for an IT firm can also spur the demand for pizzas. So essentially, when it comes to economics, every sector is interrelated. The level of interrelatedness, of course, can vary. Certain sectors are very closely related, certain sectors are not, right? So what Professor Leontiev did was, he came up with a linear equation that described how each sector distributed its output to the other sectors of the economy. And because Mark II was one of the largest computers of its day, it couldn't handle a system of 500 equations and 500 unknowns. So what Professor Leontiev did was, he reduced the problem to 42 equations and 42 unknowns. And then with bated breath, apparently just programming 42 equations and 42 unknowns in the Mark II computer took several months of effort. And it took 56 hours to solve that problem. And it was for this effort that in 1973, Professor Leontiev was awarded the Nobel Prize in economics, which opened the door to a new era in mathematical modeling in economics. Today, economics is a lot about mathematics than anything else. And I'll just read one more paragraph. This is for all those computer scientists here who think that linear algebra is mere math and has nothing to do with computing. And here I go. I'm going to read this paragraph. The importance of linear algebra for applications has risen in direct proportion to the increase in computing power, with each new generation of hardware and software triggering a demand for even greater capabilities. Computer science is thus intricately linked with linear algebra through the explosive growth of parallel processing and large-scale computations. The reason I brought this up today was, at times, we get deep into the math, we get deep into formulae without thinking about the big picture. what I want this group to always think about is the big picture. So linear algebra is not some, some abstruse, vague mathematics that we're learning just for fun. There's a larger objective. Today, if you go to any airlines for that matter, and if you were to ever wonder how is it that they make use of one aircraft that goes around India, from Madras to Coimbatore, Coimbatore to Hyderabad, Hyderabad to Pune, and maybe to Delhi in the same day, and probably comes back to Madras by the night. It's all linear algebra behind the scenes. So they use linear algebra to optimize the flight schedules and whatnot. So linear algebra is used in a lot of applications. It was always known that there were a lot of applications, but what data science has done is it has resulted in an explosive growth of linear algebra, something that never quite happened before. All right. With that in mind, let's continue with the boring stuff, which is, just give me a moment. I'm just struggling with, here we go. So we were discussing vectors. So evidently, we define what a vector is, and we also define what a point is. And for all practical purposes, there's not much of a difference between a vector and a point. So we were discussing scores in various subjects, such as maths, physics, chemistry. So you have a class of, say, 60 students, and you take the math, physics, and chemistry scores of a particular student. Now that's a vector. It's also a point. So for all practical purposes, we can interpret both vectors and points similarly. We don't need to differentiate between them. And we also talked about how to add vectors. And you just can't add any nonsense because, for example, you have this vector comprising of elements A, B, C, and then you have another vector comprising of elements X, Y, Z. And if you're adding them, then you got to make sure that A and X represent the same thing. One can't be oranges and the other be donkeys. You can't add oranges and donkeys, right? You can add donkeys and donkeys. You can add oranges and oranges, right? So take our example, the one that we were working with. ABC can be the scores of one student and XYZ can be the scores of another student, of course, in subjects such as maths, physics, and chemistry. Then, of course, you can add them like the way they've added. Likewise, we can multiply a vector by a scalar. So this is like saying, look, my scores in maths, physics, chemistry is say 90, 91, and 97. But it's out of 100. I wish to scale everything by a factor of 0.5 so that I know what's my score on a scale of 50. So the scalar C allows us to do that, right? We also looked at two interactive examples of how vector addition works and how scalar multiples work. Then we touched about what is called as a linear combination, and that's where we stopped. So a linear combination of vectors is basically this. So V1, V2, Vp are all vectors. C1 are scalars. So let me ask a question. Should V1, V2, all the way up to Vp, should the dimension of each vector be the same, or can they be different? Answers. Anyone?
I think they should be the same.
All right. Who was that?
Yes.
All right. You're right. So the dimension has to be the same. So V1, V2, Vp, all of them should have the same dimension. So what if hypothetically, it just so turns out in reality that, let's say V1 has a dimension of 5 and the other one, say V2, doesn't have a dimension of 5. Let's say the dimension is 4. So let's take this example of, again, math, physics, chemistry. So let's say there are five subjects: maths, physics, chemistry, biology, and computer science. And that's V1. I mean, you get the scores of a person. Then, for some reason, the second person has scores in maths, physics, chemistry, maybe biology, but for some reason there are no scores in computer science. So what do we do? How do we tackle that problem? Any thoughts? Can you sum it up? That's the first question. If I have a vector comprising of maths, physics, chemistry, computer science, and biology scores, and another one where I have just maths, physics, chemistry, and biology scores without computer science scores, can I sum it up? Any thoughts? Think about it. Any answer is fine. There's no hard and fast rule that there's only one answer. Any thoughts?
No.
Go ahead.
For addition, I mean, number of rows and columns should match.
That's right, but you're faced with a very practical problem here. For some reason, a lady or a gentleman doesn't have scores in computer science.
Then we can make it treat as 0.
Okay, that's one way. So there are a variety of ways you can tackle it, right? Maybe you can think of putting an average number there, right? So there are a variety of ways. Of course, each method has its pros and cons, implications, so on and so forth, right? Putting a 0, remember, when you put a 0 there, it means the valid value. It's not a null. So you're actually saying somebody scored 0, right? And that can pull down your average scores in computer science, for instance, right? So maybe you might think of, okay, let's put the average number there instead of 0. So there are a variety of ways. But the fact is, you're right. You just can't add vectors if they do not have the same dimensions. All right. So in this particular case, r to the power n basically means that each vector it's a real number. The elements of each vector is a real number. And the vector has n dimensions. That's what this says. All right. Now, we move over to matrices. Again, vectors and matrices, it can be very, very confusing. What is a vector? What is a matrix? Is there a similarity? Is there a difference? It can get really, really confusing. But there's one way to look at matrix. Can be looked at it from many perspectives. From one perspective, with just a two-dimensional array, right? Comprising of numbers. That's one way to look at it. Another way to look at it is matrices as linear transformation. So what matrices allow you to do is it allows you to take a vector as an input and transform the vector to another vector. So think of this matrix. So in this particular case, X is a vector, B is a vector, all right? And X has been transformed to B by the matrix A, all right? So here's this particular example. So there's an image, and of course, the image will have its coordinates. So you have this lovely looking kid, and you have coordinates here. We're going to keep it very simple. We're not talking about the RGB value of each pixel. So let's not worry about that. But let's say we're just worrying. So for example, you have the ears here, the eyes here, the lips here, and the nose here. And let's say you want to figure out the reflection of this image. Then here we go. You have a nice looking matrix here that can transform this image to another. So a linear transformation through a matrix can ensure that a vector gets reflected. This is one example of how you can use matrices as a linear transformation. So if you go to, just give me a moment. So this is what it does. So you have a vector here, and this vector becomes this. You see that? Here's a vector, and then after transformation, it goes here. That's how reflection works, right? If you have at the center, if you have a mirror, then each part will go to the other side, right? And this part will come here, this part will go there, right? So that's one example of a transformation. Another example, dilation. So this is again simple but interesting. What's happening here is each part of this image is becoming bigger because of the matrix transformation. So an xy effectively becomes 1.5 xy. Everything gets multiplied, right? So if the distance between the eyes was 2 centimeters before, now it would be 2 into 1.5 centimeters. So everything gets multiplied or scaled. That's another example of how you can use a matrix to transform a vector. Of course, there's an interactive. It's simple. So basically it says, look, here is a point. After dilation, what happens? Here it goes. So in this particular case, the eyebrow, which was here, is now located here. And so what has effectively happened is you moved in the same direction, but 1.5 times. And the matrix allows you to do that. Another wonderful example, rotation. So here you have an image and you wish to rotate, say in the anti-clockwise direction by 90 degrees. Here again, a matrix can help you to do that. All right. I'm not going to get into the details. It's very simple. So there is a matrix. You take x, y as an input. It gives minus y and x, which is essentially moving, or rather rotating the image by 90 degrees. Okay. And of course, there's an interactive, I don't want to call it a video. It looks like it's a JPG file that allows you to visualize this, right? Now, any questions so far?
What is the logic behind rotation here? The vector, why is it 0, -1, 1, 0?
All right. So the way it usually works is you start with this. You know you need to get here, minus y and x. Then you try to figure out what should be the a for us to get from xy to minus y and x. And you'll find that it's again a linear equation in 2 variables. If you solve for it, you'll get this.
Okay, so this is basically the vector, this is basically the matrix that you use when you want to just shift 90 degrees.
That's right. Correct. Correct.
How is the angle thing? I mean, it's just shifting positions, right? It has nothing to do with angles or something. It's just
not yet, because yes, that's because you just want to shift it by 90 degrees. Of course, you can think of rotating this by an angle theta.
The pixels. You're rearranging the values in each of the vectors.
Sorry, say that again. What do you mean by that?
I mean,
so let's look at this. Okay, let's look at the interactive so that. So here it is. So if this is the point, so what you're doing effectively is you're rotating this by 90 degrees to reach here.
Yeah. So this happens at every point.
Exactly. Correct. So every point on this image is rotated by 90 degrees. All right. Okay. So this, of course, in this particular example, it was You're rotating it by 90 degree, but that doesn't mean that it's only 90 degree that you can rotate an image
You
with.
just have to adjust the vector values there. The A vector should be adjusted if you want it like.
No, A is a
120.
matrix. Let's be very careful.
Sorry,
okay?
A matrix. Huh?
Yeah, correct. You're right. A is a matrix, and you have to. You're right. You have to adjust the matrix.
We see. I have a question.
Go ahead.
We see the transformation is happening according to the basic vector of the matrix A. That's in what
Why are you using words such as basis, etc.?
No, we see the what I can say. So for the transformed image has a that vector value for x-axis it's on 0, 1, and for y-axis its one unit is on -1, 0. So
we're not changing we're not changing the basis, are we? Don't confuse that with change of basis.
Actually, no. The matrix is transformed, and that's
the matrix is not. No, the matrix is not transformed. What do you mean by matrix is transformed?
No. The spaces get transformed, and the new space gets the matrix A as its basis vector. I mean.
Okay, let's avoid terms such as space is getting transformed. We're not even talking about that here. Right? Why talk about space is transformed? From our perspective, there is a vector, and that vector gets rotated by 90 degrees. That's it. The matrix does that. Nothing more.
Okay. At each point, this is happening.
Exactly. Correct. That's right.
What space I mean?
Yeah, you're right. I mean, you're probably throwing terms that we haven't even talked about yet. Right? So you're probably right, but let's refrain from using terminology that we haven't even talked about. From our perspective, every point here is rotated by 90 degree. So you take a point here, give me the coordinates, or rather give me the vector, apply the same transformation. The matrix, the one single matrix that we saw now, that will allow you to transform any point on this image by 90 degree in the anti-clockwise direction. Right? So that's what matrices do for you. I mean, that's one way to look at it, and I find it very convenient to look at it this way, because otherwise we'll get terribly confused about what is a matrix and what is a vector. So one way to look at a matrix, which I think is very intuitive, is it brings about a transformation to a vector, right? And after the transformation, a vector becomes another vector. That's the whole idea. So matrix allows us to do that transformation. Okay. Any other questions? Sorry. All right. Now,
we see.
Yeah, sorry, go ahead.
We can call a vector as a matrix, right?
Avoid using that.
Okay.
Avoid it. Let's not call vector as a matrix. So vector is merely a point in space. That's it. Nothing more. So there is a point in space. Now this space can be two-dimensional, which is something that we are very used to. It can be three-dimensional, which is also something that we used to, but it can be five-dimensional. So for example, if you have a class, in your class, there are 60 students. Each one of them have scores in maths, physics, chemistry, computer science, and biology. Then a vector is Sanjay's class 12 scores as represented by the scores in maths, physics, chemistry, computer science, and biology. So which means I can have a vector, I'll call it Sanjay, and I'll represent it as 93, 92, 91, 90, 97. If there is another person, Vijay, in your class, that vector will be represented as Vijay in bracket 93, 95, 97, 98, 99, something like that. Right? So What I would suggest is don't confuse vectors with matrices, because then you won't be able to differentiate between the two. What matrices do is it transforms vectors from, so when I say transformation, this is an example. So there is some vector. Here is a vector, which is represented by X here. You apply a matrix and transform it. So this is an example. The reason why I picked up this is because it's very intuitive. You understand what reflection is, right? But that's not the only kind of transformation you can do with matrices. There are a lot of transformations that you can do with matrices. So you take a vector is used by a matrix to transform the vector to another vector. All right. And some of these transformations apparently are very, very useful. Hopefully, as we progress, we should be able to understand.
Sure. Yes.
Right?
Yeah.
Any other question? All right. So now, so we have a bunch of linear equations. So the first thing we did in a previous class was not class session was we had a bunch of linear equations. We were trying to solve it. Sirisha helped us with the what is called as the reduced echelon format. How you go about. So you create what is called as an augmented matrix, and then you get to what is called as the reduced row echelon format to solve linear equations. That's one way to do it. Okay. That's one way to look at that problem. Now, there's another way to look at that problem, which is you look at systems of linear equations in vector form. So let's understand what this means. So here, take this system of linear equations. So when you say system of linear equations, it's a bunch of equations combined together, and you look for a solution to that system. So now the way you can write this system of linear equations is you can write it as, you can take the x coefficients separately, put that into a vector 1, 2, 6, y coefficient separately, put that into a vector -1, -2, -1. 8, 16, and 3 is again another vector. Now, if you go back to the idea of linear combinations, so x is a scalar, y is also a scalar. So a scalar multiplied by a vector plus a scalar multiplied by a vector will give you another vector. Let's go back to this. Here you go. A scalar multiplied by a vector plus a scalar multiplied by a bunch of vectors gives you another vector. So here, 1, 2, 6 is a vector. X is a scalar. -1, -2, -1 is a vector. Y is a scalar. And finally, 8, 16, and 3 is a vector. So another way to look at this system of linear equations is to ask this question: what combination of these scalars will result in 8, 16, and 3? Right? That is, I have a vector, I scale it by a factor of x. I have another vector, -1, -2, -1. I scale it by a factor of y. I combine them together to get a new vector, which is 8, 16, and 3. Now, what combination of x and y will get me there? That's another way to look at the system of linear equations in what is called as the vector form. All right. So here's a summary. So what the vector equation x1 v1 plus x2 v2 plus xp vp is equal to b. That's essentially, give me a moment. That's this. X, this is like a vector v1. Y, vector v2. This is like a b, which is another vector, where v1, v2, vb, b are all vectors. So imagine this: v1, v2, vp, and b are all vectors, right? Like this. Here's a vector. This is another vector. This is another vector, right? Of course, x1, x2, and xp are scalars. Here we go. Here there's x and y. They're all scalars. This has the same solution set as the linear system with augmented matrix. So in the previous session, what we did was Sirisha, she created an augmented matrix for our linear equation and solved it, right? Now, if you were to ask this question, and if you were to get an answer for what is X and Y, what you've actually done is you've actually solved this equation, the linear equation, all right? Or rather the system of linear equations. So both mean the same thing. So what we're trying to say here is, so far, we're looking at the same problem in two equivalent ways. The first one was what was discussed earlier, where you had this system of linear equations, you came up with the augmented matrix, and then you figured out what is X and Y, right? Another way to look at the same problem is look at this system of linear equations as a linear combination of vectors, and then start thinking about, okay, what should X and Y be to ensure that X multiplied by a vector plus Y multiplied by another vector will result in this new vector 8, 16, and 3. All right. So that's another way of looking at a system of linear equations. By the way, there are 4 different ways of looking at it. All of them are same. All right. We'll come to the other 2 ways of looking at systems of linear equations. Now, the next thing we want to understand is what is called as the span. Now, the way to understand span is the interactive will be very useful when we get to that. So we have a bunch of vectors, v1, v2, all the way up to vp, defined in r to the power n. Just for the sake of convenience, again, I reiterate, we keep switching between lower dimensions and higher dimensions. Always remember, when we work with lower dimensions, it is not to solve a problem. You can always easily solve problems in lower dimension, right? But it is to get the intuition right, because when you go to the higher dimension, it's only the math and the intuition that will help you. You can't visualize the problem in higher dimensions. So in this particular case, let's say v1, v2, all of them are vectors in 2 dimensions. All right, so that's easily imaginable to us. You can just imagine what v1 could be. And what this says is the span of v1, v2, all the way up to vp, which is a collection of vectors, basically, is the linear combination, all linear combinations of v1, v2, all the way up to vp. So which means if you look at this definition here, it says the span of these vectors is nothing but x1, v1 plus x2, v2, all the way up to xp, vp, where x1, x2, all the way up to xp can be any number. Think of every bloody combination that's possible for these scalars, and keep plotting those vectors in the space. Whatever you get is the span. Now, of course, it may not be very intuitive when you look at the definition. So let's look at the interactive and see if that helps us. All right, so axis here. All right, give me a moment. So what are we doing here? Here are 2 vectors defined in 2D space. So R square, right? Now what's a span? As we discussed, we look at all possible linear combinations of V and W, right? All possible linear combinations. So don't you see, I can multiply, I can keep V as the same and just play with, just give me a moment. Does this allow me to move? Yeah, play with just W, you see? I can move anywhere here. Oops, sorry. All right, then let me do one more thing. Now I play with I can now play with V. Here we go. I can go to any point. All these are linear combinations. Do you get it? Basically, all that I'm doing is just playing around with V and W, right? In linear combinations to get to some point in space. So what you would see here is I can effectively look for linear combinations of V and W and go to any point here in this two-dimensional space. Now let me ask a question. Let us say both V and W were pointing in the same direction. So if you look at V and W, they're pointing in different directions, isn't it? They don't. So W is pointing one way, V is pointing in another way. And let's say they were pointing in the same direction, both V and W. Can I cover this entire space if both V and W were to be pointing in the same direction? Anyone?
No.
Okay, that's right. You cannot. Because just imagine if V and W were pointing in the same direction, all that I can do is I can just go along that straight line, correct? Because V and W are pointing in the same direction. I can go forward, I can go behind, but I can't cover the space. All right. So that's where the idea of independence of vectors come into picture. That's something that we shall discuss a little later, not today perhaps. But if vectors are not independent, then what you can do with them is quite limited. And again, the idea of independence is very, very important when it comes to machine learning. Because the way to look at it is just imagine V and W to be features in a machine learning model. All right. If both V and W are pointing in the same direction. So to give an example, let us say V were to be the age of a person and W were to be the experience of a person. Okay. And don't you see intuitively, don't you see that both V and W would typically point in the same direction? Why? Simply because as age increases, experience typically increases, right? It's never the other way around. It's not like they're all correlated, right? So what happens is under those circumstances, you would find that V and W are not quite independent, and that has implications when it comes to designing a machine learning model, right? Now, going back. So the span is essentially, as I said, you take the vectors, V1 to VP in this case, think of all possible combinations of V1 and VP. And how do you figure that out? You take these scalars, X1 to XP, look for all possible combinations, and then see what gets generated. That's your span, all right? So the third way of looking at it, I said, there are four ways of looking at a system of linear equations. The first was, of course, the augmented matrix, which is shown in point number 3 here. Point number 2 is the vector equation, where we said x1 v1 plus x2 v2 plus xp vp is equal to b has a solution. That was the second thing that we discussed a while back. The third thing is the vector b has to be in the span of v1, v2, and vp. Would you agree? If you look at this, see, a span is, if you take vectors v1, v2 all the way up to vp, the span is in the entire space, right? Don't you see that if there has to be a solution, then this vector b has to be in the span of v1, v2, vp. I'll give an example. So let's say hypothetically, we were to point in the direction of w. I'll go again. If vector v were to be pointing in the direction of w, okay, and the point b is where my mouse is. I'll ask the question again. V is pointing in the direction of w, and the vector b is where you see the pointer. My question is vector B in the span of vectors V and W?
No.
All right. Sanjay says no. Anyone else who says yes?
It's outside the span, no?
Outside the span, of course, right? Why? Simply because V and W are pointing in the same direction. So vector B, you cannot reach vector B using a combination of V and W. There's no way you can reach, right? If V and W were to be pointing in the same direction. Okay. So going back, all that we are saying is if you can reach vector B, or rather, if vector B were to be in the span of V1, V2, all the way up to VP, then you have a solution to the problem, right? So you can figure out a way, oh, okay, this combination of x1, x2, x3, these scalars will take me to B, right? So these are three not different, but equivalent ways of looking at the same problem. Okay. So which means, so when they use the term equivalent, what they mean is for any given list of vectors, V1, V2, VP, B, either all these are true or all these are false. You can never have a situation where this would work. This is true, but the other two is false. Never, ever. All right. I'll go to the next presentation, but any questions so far? All right, I believe none. Let me go to part 2. Give me a moment. Okay. So here we go. So we're going to look at the fourth equivalent way of looking at a system of linear equations. So just give me a moment. Sorry, Sirisha, you can drop off. It's okay. Go ahead. So let A be an M cross N matrix. So what is this matrix here? Basically comprising of columns V1, V2, all the way up to Vn. Can anybody tell me what's the dimension of V1, V2, all the way up to Vn? Anyone? What's the dimension? If you look at, just read this M, exactly. So it's an M cross N matrix, V1, V2 are columns. And you're going to multiply that with a vector x1, x2. So each individual element here is a scalar. I hope you guys understand that. All right. So V1 is a column, V2 is a column, Vn is a column. All right. And x1, x2, all the way up to xn are scalars. Now, you can define this product as, it's very simple. Just take V1, treat it like a vector multiplied by the scalar x1. Take V2, treat it like a vector multiplied by the scalar x2, all the way up to, you take Vn, treat it like a vector and multiplied by the scalar xn. All right. So this is like a linear combination of vectors. All right. Now that's how you multiply a matrix with a vector. So this is essentially, okay, we are formally defining it. So what we are saying is if V1, V2, Vn, and B are vectors, then of course consider this vector equation x1 v1 plus x1 v2 all the way up to xn vn is equal to b, where x1 x2 all the way up to xn are scalars, v1 v2 are vectors. We are saying it is equivalent to the matrix equation ax is equal to b, where a is this column v1, column v2 all the way up to vn, and x is this vector which comprises of these kuti scalars x1 x2 all the way up to xn, and b of course is another vector. All right, so what we have here is 4 different ways of thinking about these linear equations. So one was augmented matrix, of course, as a system of linear equations, augmented matrix. Then we looked at as a vector equation, where you treat it as x1 v1 plus x2 v2 plus xn vn is equal to b. That's one way. And finally, as a matrix equation, where you have the matrix, you have a vector, you multiply the matrix with the vector to get another vector. So they're basically they mean the same thing, but you have different ways of thinking about the same problem. Why? From what I understand, certain ways of thinking about these problems are useful in certain contexts. That's what I understand. Hopefully, we'll get much more clarity as we progress. Right? All right. Let me stop here for any questions before proceeding. I'll probably take another 10 minutes and then leave the floor to. Do we have Kayalviri here? Because she said she'll take a session on.
Yes, we see.
All right. Okay. Fine. Any questions so far? All right. So let's do it for another 10 minutes, and then we'll proceed with Kyle's session. Give me a moment. Sorry. Okay. Now, I want you to look at this, and I want somebody to interpret this for me. What does it say? It says criteria for a linear system AX is equal to B to always have a solution. What does it mean? Anyone? What do you mean by a linear system AX is equal to B to always have a solution?
I think these are all the criteria that it should fulfill to make it solvable, or else it will become unsolvable kind of a
Okay,
problem.
but what do you mean by always have a solution? Why use the word always, A, and why was this highlighted in bold?
Because sometimes there might not be a solution.
Okay. Anything else that you can think of? Okay, let's look at the interactive. Wait, let's see if maybe not this. Here is A. This is the matrix. You have X and B. So you have AX is equal to B. So when we say criteria for a linear system AX equal to B to always have a solution, what do we mean by that? The key is for all B, for all B's. So which means we're saying if I have a matrix A And for all B's, I will get a solution, which is why we are saying, which is why we're using this word always have a solution. So if you look at this, you take any B here. The B here is this entire space. All right. You take any B here, you will get a solution for X. Take any B, doesn't matter. All right. So read the statement. It says, let A be a M cross N matrix. So forget M cross N, it's basically matrix. Okay. The following things are equivalent. AX equal to B has a solution for all B. If that is true, don't you see that the span, the span of these vectors will again be the space? Would you agree? Because otherwise you'll not get a solution, which is something that we saw. And A has a pivot in each row. Now, you may not understand this, but had you worked through the previous session where we did the reduced row echelon method to figure out the solution to a linear equation, you will find that you will get a solution only if you have a pivot in each row. Otherwise, you'll not get a solution. All right. So
We see one
Yep.
question. Pivot in the sense you are mentioning the rank of the matrix.
again, you're using terms that we should not be using here.
No,
Did I ever use the word rank anywhere? What is a pivot?
No, I was just thinking that that's what I'm asking. It's the same.
In the previous session, you remember how when Sirisha went about reducing that, she was explaining the what is called as the reduced row echelon format, right? So you take the matrix and then you do those operations. And finally, you have the ones and the zeros, right?
Yeah.
The pivot is the most, it's the leading one in a row. So if you look at, I'll give an example, since we're talking of pivots. Can you see Telegram? I hope you can.
Yes, we see.
I asked a question today. Wait. Sorry. Apologies. One moment. Struggling with. Sorry. Here we go. All right, let's take this case. The one is a pivot, the one is a pivot here. So when you take a linear equation, system of linear equation, and then you reduce. So this is A, by the way. And this, of course, is B. I mean, once you take A and B, and then you create the augmented matrix, and then you run you figure out the reduced row echelon matrix, augmented matrix, of course, you get this, right? The one is the pivot. Okay.
Yeah.
So what this says is A has a pivot in each row. So in this particular case, does A have this is A, by the way. Does it have a pivot in each row? No. There is one row where there's no pivot. So this is actually an inconsistent equation. This cannot exist. You'll never get a solution for this equation. All right. So what they're saying is, again, the same problem can be looked at multiple ways. All right. So let's look at. Okay, now look at this. This is an example where the span of these three vectors is this plane, not the entire space. I'll go again. The span of these three vectors is this plane that you get to see here, the violet color plane, not the entire space. Can anyone take a guess why? Just look at A, the matrix A. Just keep staring at it. Take a guess. The span of these three vectors is not the entire space. The moment you get three vectors, your intuition is you'll get the entire three-dimensional space as a span, but that's not the case here. It's only the plane. Why? Look at the matrix. There's a pattern there. I'll give a clue. There is a clear relationship between this column and these two columns. What is it? Look at this vector. I'm switching to the vector way of thinking. This vector, and look at these two vectors. There is a pattern there. What's the pattern? Anyone?
Because one vector is like 0, like it has no.
No, 0 is not a vector. The entire column can be a vector. What I'm asking is, look at this vector as represented by 1, -1, and 2. And then look at these two vectors, 1 represented by 2, -1, 1, 1, 0, -1. There's a pattern between, you can get a pattern between this and these two. Don't you see this vector is nothing but the difference between these two vectors? Take this vector, subtract this vector from this. 2 - 1 is 1. -1 - 0 is -1. 1 minus of -1 is 2. All right. So actually, again, we'll understand this when we do independence of vectors. So here's an example where one vector is unfortunately, one vector in the matrix itself is like a linear combination of other two. Don't you see that? This vector is a linear combination of these two. All right. When that happens, everything goes for a toss. So you thought with three nice vectors, you'll get the entire space as a span, but you didn't. All right. This is like the example where we said, the V and the W, if you are pointing in the same direction, then you'll not get the plane, right? The span will not be the plane. It's something similar. So here, if B were to be on this violet plane, would we have a solution? We would, because it lies in the span. As long as, going back to this, AX is equal to B. So we have A, which is nothing but this matrix. X is, of course, a vector equal to B. As long as B lies somewhere in this plane, you'll get a solution. But the moment if I have B here, let's say I'm just pointing here, then there's no way you can reach this point by using this matrix, by using these vectors, isn't it? You take any linear combination of these vectors, you will not reach the point that I'm mentioning. Why? Because the span of these three vectors is this violet plane. You cannot go outside this violet plane. All right. So that's an example of a solution may exist for some B, but not for all B. You understand? In this case, the solution always exists for all B. All right. You go anywhere in this space, you can find a way to get to that point in that space by using a linear combination of V1, V2, and V3. Right? But when it comes to this, you're stuck. You can get to a solution only if the point B, if the vector B lies on this plane. The moment you come out of this plane, there is no way you can reach vector B. All right. So that's the point that we're trying to make here. Okay. I don't want to get into solution sets now. I'll stop here for questions, and then I shall leave the floor to Kyle Viri, who will give us a brief overview on Git and GitHub. Any questions?
Yeah, we see.
Yep.
Can we say pivot as the one which help us to find the exact solution for that unknown values, x and y, so is.
Yes, you can say that. Correct. You can, but there's much more to that. I would strongly recommend take a matrix, go through the reduced row echelon format algorithm. It's a very simple algorithm. Do it step by step. Then you'll understand under what circumstances you'll have a solution. So for example, the one that we discussed, this certainly will not have a solution because there's no pivot here. All right. Now, had there been a 1 here, all right, had there been a 1 here, yes, it'll have a solution. But the question is whether it's a unique solution or you'll have an infinite solution. That's because there's a possibility where, so if you look at it, this is like an example where you have 1, 2, 3, 4, 5 variables and 3 equations, right? So what you will see is under those circumstances, you'll see infinite number of solutions. So what I would recommend is go through the reduced row echelon format calculation. So that process is called as Gauss-Jordan elimination. If I'm right, I think they call it elimination if I'm right. Go through that. It's a very simple algorithm that will take us from a matrix to the reduced row echelon format. Go through that, then you'll understand under what circumstances you'll get a solution, under what circumstances you'll not get a solution, right? But yes, you are heading in the right direction when you said that.
Yeah, got it.
Yeah. Any other question? All right. If there's nothing else, then I shall leave the floor open to Kyle Viri. Go ahead, Kyle.
Yes, yes.
You may have to be a bit louder if you don't mind.
Shall I share my screen?
Please, please. Do I need to unshare for you to share? Let me just stop sharing. Go ahead.
Is my screen visible?
Yes, it is, but you might have to keep your microphone close to your mouth.
So in this discussion, I have first assumed that everyone would have a GitHub account and Git installed, because that would not be covered
Okay,
here.
no, but before that, what is Git?
Yeah, I'm starting with it.
What is GitHub and what is Git? You use two terms. What's the difference between the two?
Is my presentation visible or still the Chrome screen?
Just a Chrome screen. I don't see your presentation. I still don't. Yeah. I can see I can see you, but I don't see any. Yeah, I can see that.
Oh.
Yep, go ahead.
So GitHub is actually a repository. It consists of many repositories, which in which we can perform version controls, and that is the actual application.
Okay, what is
It
version
is-
control?
And if we come to Git, it's a
No,
command line interface.
no, what is version control?
A version control means we'll be working on, if we take for an example, if you're working on some projects, first initially we'll be developing for example version 1 application. it will be with some basic features. And then we'll be adding some more features. For example, let me take as I'll be changing a button color and I'll be releasing a new version. So we need to save those version, and also if I found that my users does not like the new feature, then I must able to revert back to the older version. So if I have that control to move from a new version to previous version, I also have some system to store all these versions in an efficient manner, then it's a version control system.
All right. So
Okay.
why
So
should students, those who study in college, have an account in GitHub?
in GitHub.
Why?
Uh,
I know I'm
I
digressing,
think
but I think it's important for us to know. Not just
Yeah.
students, even people like me should have an account. I don't. I have one, but I rarely have anything in my repos, but still. But why should students have, students for that matter,
Yeah.
anyone for that matter, why should they have an account?
my knowledge, I think that to showcase our projects or what am I working with, because it shows our recent commits, like at each time what I did, everything. It is like some resume which has, like, for a long time it will be noting out what all
Okay.
I'm working on.
All right, fair point. Let me explain in a nutshell. I've seen two instances. I've asked people, can you show me a project? One answer that I get is, oh, that's in a different laptop. That's one answer that I get. Then I ask them, okay, why don't you just share your screen and show it on that laptop? Then 90% of the answers would be, oh, I lost the project. It's not there in the laptop, right? Once lost, it's always lost. So at least GitHub allows you to maintain your code at one place and that will stay there forever. Number one. Number two, I have seen so many recruiters. So when I send resumes, they come back to me and say, there is nothing in their GitHub account, right? So many recruiters have told me that. So it's important that you have repos. So if you take Bhargav's profile, I think there are about, 600 repos in Bhargav's profile at the moment. If you go to his, I think it was 565 when I saw it some time back. Maybe it's much more now. All right. Yash, can you just look up Bhargav's GitHub while we speak? Let's share it so that people know the kind of stuff that people maintain in repos. So that's another thing. The third thing is, I have seen recruiters coming back and saying, where are the commits? So, Kyle, can you show your GitHub commits? That nice little screen that shows the commits. Yeah.
Sorry to interrupt you, VC. I just want to share an experience of mine when we were hiring.
Go ahead.
So we hired for a full stack developer, an intern role at our place, right? So we got a lot of profiles. Actually, I got this idea back. I watched a YouTube video and then I suggested them that. What is it? I asked them to look at the GitHub, the tile that they have, the commits they made, right? So we had 3, 4, 5, 7, like a lot of profiles. When we looked at it, people were like, pushed it on day before or day before yesterday just to make sure when they attend the interview, it is there on their profile. But we saw very rare profile that has, a constant commits that been happening weekly, twice, thrice. You should see that in the
Yeah. Let's see Kyle videos. Kyle, why don't you just share your GitHub profile? I know I am diverting, but still it's important for people to understand.
Is it visible?
Yeah, it is. But how do I see the commits? That nice little dashboard.
Where it will be?
What is your?
These are my repositories.
No, wait. Go to overview. Click on overview. I'll tell you what recruiters do. Just scroll down. You see? So you had a bad time in December, January, February, March, there was one commit. April, no commits. May, no commits. Simple, no shortlist. As simple as that. Right? This has to be littered literally with that green stuff throughout, which will tell the recruiter that you are committing. Of course, this can be gamed. You know, you can commit some random stuff. That's also possible, right? It doesn't check whether you're committing proper code. It doesn't check that. But the more green this looks, the better signal that you're giving to your recruiter. All right. So don't just think that GitHub is merely a version control system. It's much, much more than that. It's also your, okay, yeah, I have Bhargav's.
Can I share Bhargav's screen?
Yeah, I have it with me. Give me a moment. Let me just share.
Sure.
Give me a moment. I think it's much less now. Did Bhargav remove his repos? I just see 163 now. I don't know.
Maybe you must have seen the commits he has done. He has done so much with other people.
Ah, okay, probably. So here we go. So this is Bhargav's profile. See, he hasn't committed anything. Of course, he doesn't need to care about. He's gone beyond the stage where somebody is going to look up his GitHub commits to offer him a job. Okay, so he's going to use his network. You know, nobody's going to look up his GitHub commits. But the fact is, he has about, you know, he has 163 repos, and that conveys, you know, that sends a message that he's at least at some point in time he was a serious coder. Maybe if not now, right? Kyle, go ahead.
What does stars represents? We see.
Sorry, what does it say? Stats, is
What
it?
does stars? He has 342 stars.
I don't know. What is it?
People,
what does it mean? Yeah, I don't know, but others, what does stars mean?
people started. It's more of like.
Oh, like okay.
Yeah.
Okay. So it's like people following you and liking your code.
Yeah. And people always look for version controls. Like when they hire people, they always look for how you can control your version. If you don't have constant commits, then how you think they can hire you for version?
Bhargav tells that he always sees a person's GitHub. If he's hiring for a coding role, he sees this pattern, and only if they had committed, he'll then move on to hiring.
And it also means that someone can easily take out the code and then commit it a day before, right? So they always.
But still, he puts that efforts, right? So you can see.
All right, Kyle, go ahead. You can share your screen now. I know we were digressing, but still.
So the brief definition for Git is, it's a distributed version control system that enables efficient tracking of changes in source code. So here distributed means having your source code in a centralized host. It means in a main branch we'll be having our source code, and many developers who are all been working on the same project can get the source code and replace it in their system and can work on it.
So question again. So Git, does that reside on your machine or does that reside on a cloud? Let's say you and I are working on a project. All right.
Okay.
So we have an account, and both of us have an account in GitHub, and we have decided to collaborate to work on a project. Okay. So do I need to install Git at my hand, and you also need to install Git at your end?
Yes, we see. We have to, both of us have to install.
Okay, so both of us have to install Git. So question, without installing Git, can we collaborate and work?
It's not like only Git. I think we can also use command prompt, or if we are in Apple or Linux, we can use our terminal. For Windows, Git is more recommended.
So what does Git do? How does it help us collaborate?
It's just for the interfacing using the GitHub through command lines. We can also use through graphical interface. It's another mode.
All right. So what you're saying is, it's like I maintain the code in my machine. The code is also there in GitHub, which is on the cloud, correct? The one that we saw now,
Yes.
right? And I keep punching in my code on my machine. You also keep punching your code in your machine. And somehow our code has to move eventually into GitHub, right? So it's like keep syncing up what is there in my machine with what is there in GitHub. Is it something like that? Git allows us to do that. Is that right?
Yes, we see.
Alternatively, I could avoid using Git. I can write my code and then I can go to GitHub. Log into GitHub and then I can move my code too. Is that right again?
Yeah, of course. Both is possible.
Both is possible. Then why use Git? What's the advantage of using Git?
This is easier than the graphical user interface. You don't have to log in every time. And
Okay.
also,
And
while
then
working on the
go
what
ahead.
I found is while working on the image classification project, while directly uploading our files, Git has the limitation for 25 MB. While pushing, we have 100 MB limit.
Question.
File size.
So if there is a code on GitHub, all right, and if I am modifying it and you are modifying it, how do we manage it? Both of us are
That's
working. So how do we manage it?
actually we have that's for distributed means we have many branches for a single project in a single repository. The main branch contains the source code and we'll be working on some other branches for it. Both have independent 2 branches.
Okay, so when you say a branch is like a copy of the main code, main branch.
Yeah.
All right, so it's like I work on my branch, you work on your branch. Is that right?
Yes. After everything is finished, we can merge them. We can compare and merge them.
So who will do the comparison here? So you and I have to sit together and then compare, is it? How do we effectively decide? How do we move the code to the main branch? So let's say there is a small piece of code. Both of us are working together. It's quite possible that effectively I might be overwriting your code in my branch, and you might be overwriting in my code in your branch, of course. So how do we ensure that which one goes to the main branch?
We can try to merge our branch. So if we find any conflict, we can first rectify that and then we can move to the main branch.
So is that automatic, or is it that you and I have to sit together, compare the code, and then decide which one goes to the main branch?
No. Any one of us can give the command for the merge and it will do the comparison. The Git will do the comparison.
No, the comparison is fine, but who decides? How do we decide which one goes to the main branch? See, I can also try to push it to the main branch. You can also try to push it in the main branch, isn't it?
Yeah.
So which one goes? How do we decide?
If it to decide which is the best code, then Git cannot decide it.
So a user has to decide, is it? Some user has to decide which code is the best code. Okay. All right. Go ahead.
Sorry to interrupt. I'm so sorry. Branch is not something like it creates. It's like a pointer. For each commit, there is a pointer that points to that commit. Right? Branch is not something it creates different replica. It's like each time you commit something, you push something, it will create a pointer that points to that commit. And yeah, it's like that.
It need not be a replica of the code. It can be a part of whatever you're trying. It can be a feature of your product and you just merge it with the main product.
Okay, Rakesh had to say something. What is this pull request, Rakesh?
Request too much.
Rakesh? You can't speak, is it? You don't have a microphone. Okay, it's okay. There's no point really typing. That's not going to help. You need to create a pull request to merge branches. I still don't understand what is a branch. So what's a branch? Can someone help me understand? Is it a copy of the main code, or what is it?
It does not have the actual copy actually. It means it does not replicate them. We will not be having 2 memories.
Mm-hmm.
Only the changes will be stored. Like in main,
Oh,
apart
okay.
from the main,
Okay.
what all the
Okay.
changes will be there, and that will be.
Okay. So which means there's a main code, and then I play around with it. You call that a branch where what is effectively stored or tracked is the changes. Am I right?
Yes, yes.
Okay. All right. Go ahead.
So,
What is forking? I keep hearing this word. You can fork my code. You can fork my code. What does forking mean?
I don't know. I see.
Never heard? Anyone?
it's like bookmark.
Is that so? Forks. F-O-R-K.
It's like you bookmark. Yeah, it's like save for later, bookmark my code. Something like that.
Are you sure?
I think.
I've seen instances. Wait.
Sure. Let me check. If I'm wrong, please correct me. Others.
Anyone here who knows what forking means? None, is it? Okay, fine. Go ahead, Kyle.
I think fork is what you call the replica of the main repository.
So it's like,
At least that is what I read. Yeah.
okay, Rakesh, what does Rakesh have to say? Let's see.
Forking is copying the original code without affecting it. Whatever changes you have.
Correct.
So you should
correct.
never work in the main branch. I think you should always you should never work in the main branch. That's a good coding practice. So I think that's why you fork it and you make the changes before, making any changes in the source code.
Okay, so the question, what is the difference between forking and the other thing that,
Branch.
yes.
So forking, here you take the complete source code. So you use branch when you want to fix, for example, branches can be different things. You have a main source code, and say if I have a bug and I want to correct only that part. So I'm writing a code, and after I fix it, I just merge it with the main branch so that my bug is rectified.
Hmm.
And you can add new features, everything. So a small snippet, you can say it's a small part of main code that you want to add or remove something.
And forking is, so when do you fork and when do you choose to branch out, if I can use that term?
That I'm not sure. I think Rakesh is the right person to answer that, given he's putting everything.
What I have seen is, I have seen creators of software. So if I create a new software altogether and I load it to GitHub, then I would tell the open source community that, okay, you may fork my code and create your own versions. Exactly. Branching happens in a closed project, forking happens in open source communities. So good point, Rakesh. Unfortunately, you're not on the mic. I wish you were. But so what Rakesh is trying to say is, let's say, okay, we are working on some of these projects, right? Say, for example, the Idli Vada project. And if we were to work collaboratively, then we would do branching. Rakesh, if I'm wrong, just say I'm wrong. You can type it, okay? But let's say I create a software, an application, and I release it to the open source community. And then I tell them, okay, now this is something that I worked on. You may work on it further. You can create your own versions. Then we're not doing anything collaboratively, because of course, it's quite possible that someone else might create another software on top of what I've created, and then I might use some portion of that, blah, blah, blah. All that is there. But effectively, what we're doing here is I have created a software and I've announced it to the world, to the open source community, to fork my software to create their own versions. So that's how I interpret it. Rakesh, would you differ? Okay, you've shown the thumbs up, so I believe yes. Okay, thank you. Go ahead, Kyle. Sorry for interrupting, but I thought it will be useful to get that clarity.
Yeah.
Go ahead.
So
Again, Kyle, let's not get into commands and all that. Brief, what is more, that is something that we can always learn, Google and learn. But the principle is what is much more important for us, so that we know why the hell are we using GitHub and why the hell are we using Git. I think that's much more important. So go ahead.
okay. So with this 2 points, where one is the Git is distributed and the other is it can do version control. So this we can get an efficient tracking of changes. It means with the version control, we can save all our commits. Yes, when the commit has happened, and it is also given for each commit a SHA code is also being generated, so we can keep track of our each commit.
Sorry, what is generated? Say that again.
SHA number, SHA ID or something.
What's that?
With each commit, we'll be getting a unique ID for them.
Okay, all right, go ahead.
With that, we can efficiently track our changes. And next, why we need to use Git?
Okay,
First,
I think we understand. I think we understand this now. So go ahead. Next.
After this, I've only given the code.
Okay, it's just the code. So let's not worry about codes, because that's something that people can Google and then they can figure out. All right. Anything interesting that you wish to share apart from the commands that are used to?
I have a doubt here.
Go ahead.
I mean, locally when we use VS Code or something, I know we can use some Git or controller that we have locally to push code. But if I use Google Colab or Jupyter Note, how can I push my code into GitHub, or how you do that when you code? Because I've seen people posting GitHub links in groups. So you can just give me some idea.
Good point. Anybody here? Anyone?
Actually, we can drag the file. We can keep both the tabs adjacently and tab the file from the folder and push into the GitHub repository.
You upload it directly from GitHub without the command line.
Yeah.
But I think in Google Colab you can have you have extensions, right? I'm not sure. I've never used, but I think in Google Colab you have.
I'm not sure.
So what extensions are you talking about? What does it do?
So basically in VS Code, instead of having Git as a separate app, in VS Code you have these extensions which you can, I mean the third party applications where you can push your code from VS Code editor, any local editor. But she's asking for Jupyter Notebook and Google Colab. I think
so which means your code is on the cloud, such as, again, Jupyter Notebook can be on your machine, right? So that's like any other. What's the difference? I mean, Colab I can understand. Colab is on the cloud. Jupyter Notebook is on your machine right now. Isn't that like any other code?
Oh yeah, correct.
All right. So what Pavi was perhaps asking was the case where the cloud, where the code is on the cloud. Maybe a Kaggle notebook or a Colab notebook. And then if you want to move that to GitHub, is that what Pavi was asking? Is that what?
Yeah, if it's on, yes. If it's on cloud, then yeah.
All right. Anyone else? Anyone here who knows? How do you do that?
You can download the file in the Google Colab as .py notebook.
See, that of course we know. I mean, that's a two-step process, right? You download it to your machine and then you move it to GitHub. That's okay. Is there another way to do it? Where it's there in the cloud and then you move it from. For example, I have seen one case, not entirely in this context. There was one case where we uploaded the code to GitHub. Then an entirely different application called Streamlit. It was a web application that sits on another cloud that could read the GitHub code compile it. I shouldn't use the word compile. This was Python code, so you don't use the word compiling. It basically takes the code, runs it, and then renders an application. Now, I did one thing, just for the heck of it, I just changed the GitHub code, and immediately in a few seconds, the web application, it managed to understand that there was a change in code, and then there was an appropriate impact in the web application. So I've seen that, but I think Pavi has a very valid question. If somebody gets to know how to do that or how it is done, that will be wonderful too. All right. Okay, so Kai, I'll do one thing after this call. Just share the presentation in the group so that people can have a look at the basic commands. Okay, and if
Yes,
anybody has a
okay.
question, you can ask the question in the group. Collectively, I think we can answer them. All right. So let's not get into individual commands. That's not the objective here, but broadly, all of us need to know why should we use Git and why should we use GitHub. I think as long as we understand that and the terms, that's good enough. Anything else that you wish to share, Kyle, on Git and GitHub?
Just now I saw there's an option to save my code in GitHub in the Google Colab.
Sorry, GitHub to Google Colab, is it?
No, there's an option save a copy as in GitHub.
Oh, okay. So which means you can write a code in Google Colab and then you can save it in GitHub. An option is there in Colab, is it?
Yeah, that's an option.
Are you seeing something in front of your eyes? If you can share.
Yeah.
Can you please?
Yet I'm not. It's asking for to sign into GitHub.
Oh, okay. So it basically connects to GitHub. Okay, so it basically links your code to a repo in GitHub, I suppose, right? So the moment you change your code in Colab, it allows you to. Okay, I get it. Okay, all right. Okay, cool.
Hey, thanks. This works.
Try this, Kyle. You anyways working on this code, so create a repo. You must have created, right? I suppose. Have you?
Yes, yes.
All right. Try not now, but a while later.
Okay.
Just sync up your Colab with GitHub and see how it works. That will be lovely. All right.
Okay.
Okay. Anything else?
Yeah, I have a doubt.
Go ahead.
Yeah. When we download a file from GitHub, it takes much amount of data. But when we clone it, it takes less amount of data. How does this possible?
Am I audible now?
Yes, you are at last. Rakesh.
Yeah. For that question, when you download a file, it will come with the dependencies and the libraries. And if you clone it, you need to install the dependencies and the libraries. So you will run in Node, you will run npm install, and in Python, you will install the requirements.txt file. So that would add the weight when you install it.
Yeah. So you have the dependencies that makes weight in the project, right? When you download.
Yeah.
Okay, sorry. A new term, clone. What is clone? I know what is a fork. I know what's a branch. What's clone?
Clone is like running it in your machine without creating a branch. You are working in the main branch, and you can update the main branch with that thing itself. You don't need to give the initial commits. Like you don't need to specify the path to the repo. While cloning it, it automatically initiates the path to the repo, and you can work on it.
Simple. I need a more.
Okay.
I need an answer for dummies like me.
Okay.
I understood fork. That was a good answer that you gave. I understood what a branch meant. So collaboratively, you and I are working on a project. I create a branch, you create a branch, and then we
once you clone it only, you can create a branch. Without cloning it, you can't create a branch.
Oh, is it so? They're related, is
Yeah.
that? Cloning and
Yeah.
branch. Okay. So when I clone, what happens?
Does it? Do you not get the code into your local machine? That was my understanding about cloning. The
Sorry?
repo. When you clone a repo, do you not
Yeah.
get it on your local machine?
We will get it on the local machine, like wherever we want it. Even in a VM or in a local machine, you can clone it and get it, and then create a branch and then work on it.
But when you work directly with branches, you're directly working with the.
No, we can we can't directly work with branches without cloning it. We have to first clone it. Then only we will get access to that particular repo. Just I will show a repo. So if this is a repo,
No,
and
we're not seeing anything.
oh, sorry,
Please.
sorry, just a minute.
Sorry, but clone is something that you call download technically in Git, right?
Wait, I will share. Okay, so here you will get that repos ID. Like this is the repos URL, and when you use git clone in it, you will clone this repo, and you will be directed. If someone called Latish is using this repo, he will clone it, and he doesn't need to initiate. Like he will push the code to my repo. Like it is collaborating. When you clone it, only you can create the branch. Without cloning it, you can't create a branch.
No, I understand, but
Yeah.
Break down clone. You should not use the word clone. Use some other word.
Okay. It is duplicating. Like
is it duplicating?
The code. Yeah, duplicating the code in my machine and using it.
So which
in
means
my
you
machine
are literally copying the code to your machine. Is that right?
In my machine or even in a VM.
Oh, whatever.
VM is
whatever. So which means when you clone, you are copying the code to your machine. Then what is a branch then?
Branch is like copying the code, and we work on it. We work on it and then add it. It is not. It is mandatory, but in some cases, if the people working is the count of the people working in a team project is less, let us consider 2 people. We don't have to create an extra branch and do a merge to that thing. Like create a pull request and do it. We can work on the same main branch. We can create. We can push, and the Git itself creates a merge request. That's like I will put it in layman terms. When the amount of people are working in a project are small, you can clone it and you use the same branch itself. When it goes in a large number, you should branch it, because your code will affect others code, and you can't directly merge it. You need a senior dev's support or a permission to merge it. You need to create a pull request to the senior dev. So the pull request will notify the senior dev, and he will sort the merge conflict. So if my code have code in that particular page has 10 lines, and another person's code has particular on that particular page is 20 lines, the senior dev will look into that, and he will clear the conflicts.
Oh, okay. All right. So the pull request is sent to the senior dev, is it? So it's like once I have finished my work, and let's say you have finished your work, and both of us are working on the same thing, unfortunately. So I shall ask, who will give the pull request? Is it something that
the developer who is creating who wants to merge the branch will create a pull request with the branch?
Okay, so it's like telling the senior dev the senior dev that, look, I've finished my part.
I have
do your bit to merge it to the main branch or something like that. Is that what you're saying?
I have finished this particular feature, and we can put it in this way. We can create a branch to finish some features, like particular feature. If it is a chat feature in a software, we can create a particular branch for that particular chat feature, and we can use that. If a project has 4 modules, we can create 4 separate branches and work on that 4 separate branches.
But to create a branch, I need to
You
clone.
have
I have
to
to clone,
Yeah.
which is essentially copying the entire code to my
entire code and all the branches. If the project already has 10 branches, the clone will create all the 10 branches in your machine itself.
Okay. So which means I can actually see the state of, so if other people are working, I would know where they are. Is that what you're saying?
Yeah, you can visit the branch like
okay.
You have that option like viewing the other branches in the Git directly.
Have you ever worked on something collaborative like this before?
Yeah.
You have.
I have worked in Bitbucket. Bitbucket is more user friendly than GitHub, but it is for it is more for a private repos, more of a private repos.
Okay. Not the open source ones.
Yeah.
Okay. All right. Okay. Thank you, Rakesh.
Yeah.
Anyone else? Any questions?
Yeah, I would say, I got this today evening when I was coming back. I thought it's kind of an open discussion that you can think about it and post it in the group. What I thought was when Git Copilot was launched, VS Code just added as an extension. It's more of like you can have it in your code, and whenever you make a mistake or something like that, it will help you assist with your code and everything, right? Now that Microsoft have access to ChatGPT or OpenAI entirely because they hold a lot of stakes, what if they will create an extension or something like ChatGPT, which they can integrate into VS Code and it will give me the code whenever I ask something. It's like merging VS Code and then ChatGPT or OpenAI's API, and then it's like it will take care of everything. I just have to push, maintain the code. So
Okay.
I just got
this was okay. Your thoughts, was it?
Yeah.
Okay.
Can think about it like and post it in the group like what will happen, what's the impact, something.
Anything else? Any other questions, folks? All right. If there isn't anything else, we stop for the day. Meanwhile, on Monday, we will continue with the linear algebra. Strongly recommend that you go through those slides that I sent. Merely watching videos doesn't help when it comes to linear algebra. So that's one. And let's also discuss what else are we going to do on Monday over the next 2 days. We shall discuss that in the group. Thank you for your patience and have a great weekend. Bye.
Bye all.
Thank you.